So today I'm going to talk about dimensioning. Dimensioning is a way of specifying your projections. If you remember, we were talking about projecting in the last couple lectures. Projecting orthographic views, isometric views. Well, they don't mean anything without dimensions. And this lecture is going to be about dimensions, as far as where do you put the dimensions. There's all kinds of different rules and things that you got to think about. You can't just do whatever you want. So we're going to talk about that process. There are many different kinds of drawings in the industry. One is for the architecture industry, where the dimensions are slightly different. They don't really have arrowheads. The symbols are really simplified. The tolerances are like plus or minus a quarter of an inch. Okay, it's just a different industry. This is one type of drawing. Then you have a PCB layout for the electronics industry, okay, where there's not even any dimensions. It's all like just based on chemistry and photography. And then there's the drawings you see in mechanical engineering, where you have arrowheads, you have certain specifications, certain styles of lines and things like that. And this is the type of drawing and dimensioning process that we are going to study. The first way that you can dimension a mechanical drawing is by using ordinate dimensioning. And a lot of engineers and machinists like this because it's simple. If you look at this technique, there's no arrowheads, there's no extension lines. It's very, very simple. There's no dimension lines. It's very, very simple. And here's how it works. You set a zero, a point of reference, and everything from there gets a number. Okay, so everything is referenced about this point. And the nice thing about this is, like I said, not only is it simple for the engineer, but for the machinist, it's very easy to program. Remember, when a machinist takes a drawing, they got to program it on a CNC machine using G-code. And when you program with ordinate dimensioning, it's really easy because you just plug in these Cartesian coordinates onto the G-code and there's no math. There's no, going like, all right, what is this distance? It's this minus that, and then get all kinds of stack up errors. So this technique is very, very common and very favorable by many professionals. The next type of dimensioning is called tabular dimensioning. This is something you see in a lot of catalogs and engineering textbooks. And anytime you have like a generic model that comes in different sizes, usually you use tabular dimensioning. And the way it works is you put the generic model as a diagram and then you put a bunch of symbols like internal diameter, ID, or outer diameter. And then you put a table here that shows all the different sizes for the different numbers. So this is an easy way to communicate a lot of different sizes in one place. The next type of dimensioning technique is called GD&T, geometric dimensioning and tolerancing. And that's what you see here. You see all these symbols? That's what this technique is. And the purpose of it is to help reinforce the things that may not be so obvious. For example, if you look at this circle, you don't know how circular it is. It's like the Earth. Is the Earth a perfect sphere? No, it's not. When you really study the Earth, it's like this distorted egg, this distorted ellipse in every dimension. So that's the same thing. When you study a geometry, when you zoom in, this is not really flat. This is like a zigzag. This is like a mountain range. So GD&T is to help reinforce some of these geometric entities that are difficult to control with just regular dimensioning. Usually GD&T is not used so much for custom machinery or 1Zs and 2Zs on fixtures and things like that. It's mainly used for high volume manufacturing for various reasons. First of all, not every machinist is familiar with GD&T symbols. Second of all, whenever you spec something like this, a lot of times you have to design custom gauges to control this. This is not a simple specification. Okay, you're putting references on datums with certain tolerances. You need to design a special fixture just to test this. So this is mainly used in high volume manufacturing products. Usually the quality engineer is the one who works with this because you really got to understand geometries when you work with this. This becomes kind of complicated. This is a skill set in itself, though. I knew a couple engineers who actually did this full time, so this can require a bit of knowledge and a bit of experience. I personally went on training for this for 1 week, and it does take a long time to really understand the skill set. But for this class, what we're going to do is just stick to standard dimensions for several reasons. One of them is that most people are familiar with this, and you can do a lot with this. You can design a lot of different machines and fixtures that are universal throughout the industry. So we're going to focus a little bit on using this technique. But before we start, we have to understand units and standards, and they both are two different things. Units is talking about the scale of your numbers. It's talking about how big is it. For instance, is it 1 inch? Is it 1 feet? Is it 1 millimeter? Okay, that's the first thing you got to specify. The second thing is the standard. The standard talks about how does it look like? How do the arrows look like? How much of a gap do you want here? How does the value look like? How is it spelled? What direction is it spelled? So there are many different kinds of standards. The ISO and ANSI are the most common ones. Most of the companies in Northeast Ohio use the ANSI, so we will stick to this one as well as the SI system of units. But just understand, based on the industry that you work at, like for instance, like the aerospace industry tends to be a little bit more international, so they would use maybe the ISO standard. And there are many other standards out there for the military, for the marine industry, for certain research industries. They have their own sets of standards. But again, in this class, we're going to stick to ANSI and SI. And again, the reason I mentioned this is because anytime you create a new file in SolidWorks, a part file, an assembly, or a drawing file, you have to set these two things and save it. Otherwise, you'll get problems. You'll get intermixing problems, and that's not good. And I'm sure you've all heard of this conversion issue, right? This is probably the most famous and most expensive unit conversion mistake that's probably happened in history. And I don't want to be cliche and go over the same stories you hear in every engineering class, but again, you can't stress that enough. You got to understand the units, and this is going to affect you on your assembly. Sometimes you may be building something in inches, then you're going to import something in millimeters, and then you realize you got to start over because sometimes the scaling tools don't work as well as you like them to. So remember, on every file, double check the units that you're using. And I'm going to teach you how to do that. I'm going to teach you how to set that up once we get to that stage of the program. The next thing we got to learn are the line types. There are many different lines to specify a dimension, and we're going to study these. The first type of line is called the dimension line. You see this? That's what I'm trying to show in blue. Okay, it's got arrowheads, it's got a value, okay, and that's what it looks like. Then you have extension lines. They extend about 1/8 of an inch on the ends. But again, you don't have to memorize all this because all of that is saved in the software. All right, but I'm just letting you know. Gotta have a little gap coming out of the object, and gotta have a little gap extending out. You also have leaders. Leaders are kind of like dimension lines, but they're used to specify holes, surfaces, fillets, and things like that, or knurls. And you can specify them with an arrow, a dot, or nothing at all. The arrow is a little bit more descriptive than the other ones, and I highly encourage you to use this. The type of arrow that you want to use is this one. And again, this really depends on the standard. But like I said, for the ANSI standard, this is what we're going to use. If you use a different standard, maybe this is what's acceptable. I'm just teaching you about the ANSI standard. The arrowheads can be placed in many different ways, like you see here. This is the standard, okay? But sometimes when you run out of space, you put them on the top of the extension lines, like you see here. You can also move the dimension to the outside, like you see here. But then you lose a lot of space, a lot of dead space here that you can use for other things, maybe smaller dimensions that go inside. So this is okay, and you can also put this like that over here and then keep the arrows outside. So again, you don't remove that dead space. When you letter on a drawing, you want to stick to capital letters and you want to remove the serifs. You see all these serifs? You want to remove these because they're not necessary. Remember, on a detailed drawing, you're trying to be as clear as possible, and you don't want to include more. You don't want to include more that may distract from what you're trying to communicate. What you're trying to do is communicate everything as clearly as possible and with just what you need, okay? You don't want a gold plate. You don't want to add more than what the customer needs. You don't want to add more than what you need to machine, you need to fabricate for your design to be successful. So stick to capital letters and stick to a sans serif font. Also, there are many symbols that are used in a drawing. Okay, we're just gonna focus on the basic ones like you see here. And there are thousands more symbols. There are electrical symbols, instrumentation symbols, pneumatic, hydraulic symbols, floor plan symbols on utilities and things like that. Okay, there are thousands of symbols that are used on drawings. Surface finish welding. Okay, the list goes on. But let's talk about just some of the simple symbols that are used to design custom fixtures and machines. So now that we understand a little bit about the line types and the lettering and things like that, let's talk about the assumptions. You have to make assumptions on a drawing, otherwise you will crowd your drawing with specifications. So there are some things you have to assume so that we have some space to specify the more important items in the drawing. So let's talk about what is assumed from a drawing. The first thing is, if it looks perpendicular, it is perpendicular. So you don't have to put a 90 degree. If it's 89.9 degrees, then you do have to put a specification. Otherwise, the machinist is going to assume it's 90 degree. If you need a particular control over the perpendicularity, then you can provide GD&T symbols like we talked about. Okay, so just remember, anything that looks perpendicular or parallel is perpendicular or parallel. The next assumption is symmetry. If it looks symmetrical, it is symmetrical. But personally, I don't like this assumption. I feel like it's a little risky. So what I do is I include a center line and connect a CL symbol. This should actually be connected to it. Center line can not only be used for communicating circular features, it's also used to communicate symmetry. Another way you can do this is to add a datum feature. A datum feature is just a way to reference a line, to give it a name. You put a datum on a center line like that, and you put a note to say all features symmetrical about this datum. Okay, so that's just two ways to reinforce symmetry. But technically, something that looks symmetrical is supposed to be assumed to be symmetrical. Finally, the third assumption is that anything that looks straight is straight. Anything that looks circular is circular. But again, if you want to reinforce the circularity, you got to use GD&T. Okay, otherwise they're just going to assume that it's what it is. It's a circle and it's a straight line. This is flat and things like that. Okay. So now that we understand the assumptions, let's talk about some of those rules that I talked about. Some of the guidelines on where you can and can't place dimensions. So again, a lot of these rules need to be broken, and that's alright. The goal is really clarity. A lot of times I'd ask professionals like, hey, what's the rule on counterboards or that? A lot of times they say, hey, forget the rules. What is clear? Okay, that's what you gotta understand. Does it add clarity? So my goal is to kind of give you a little background on these rules, and then hopefully you can use that in the industry and help add clarity to the drawings. Because a lot of technicians, machinists, and engineers, they're familiar with some of these rules, so it's good to stick to one technique so that we are all on the same page, so that there's less guessing. And when I go over these rules, I'm going to be honest as far as which one is ironclad and which one is more like an academic kind of trivia kind of rule. Because I remember when I was starting out, I thought all these rules were ironclad, and then they'd ask me on the job, they'd be like, hey, review this drawing, review that drawing, and then they'd say, oh yeah, that's just what they teach you in school. No one really cares so much about that. So I'm going to be honest on the things, on the mistakes that really can cause problems on the shop, and then the other items that are not so much of an issue. So the first rule says to not dimension hidden lines. That's as simple as it is. That's it. Dimension solid lines, dimension center lines, don't dimension hidden lines. If you want to dimension a hidden line, create a section view and dimension the solid lines inside the section view. This one's a little gray, okay? It's not ironclad, but again, it's about sticking to a standard that is well understood and that maintains clarity. So again, try to avoid dimensioning hidden lines as much as you can. The next rule is about cylinders, positive cylinders and negative cylinders. Okay, so positive cylinders like a rod or a dowel pin, negative cylinders a hole or a bore. And this is saying that When you dimension a positive cylinder, use a longitudinal dimension with the diameter symbol like you see here, as opposed to a negative cylinder. A negative cylinder gets a liter. You see that? You get a liter with a diameter symbol. So a liter for negative cylinder, longitudinal dimension for positive cylinder. And it may not make sense as to why we're doing that now, but later when we learn about fastening features, when we learn about how to spell out fasteners in drawings, we're going to learn why using a liter makes a lot of sense for a hole. Because with just 1 liter, you can communicate so many specifications like threads and thread depths and bores and counter bore heads and things like that. You can communicate a lot of specifications in one shot, as opposed to putting a bunch of dimension that may crowd the drawing. So if it doesn't make sense now, just remember at least that for a negative cylinder, use a liter and use a longitudinal dimension for a positive cylinder. When you do use a liter for a hole, make sure that the liter aims towards the center of the hole. See, this is bad. Now the software is going to do this automatically for you, but I remember during the drafting days, you'd get points off for this. Okay, so make sure that the liter points to the center. When you want to dimension a fillet or a round, which is what you see here, you can do it 3 ways. Like this, like that, or like this. So try to pick one that makes sense and makes sense for the drawing. Alright. Sometimes I feel like a generic note is a little risky, because sometimes I modify a fillet on a drawing and then I forget to put a specific dimension. So just try to pick something that makes sense as far as maintenance and as far as readability. Grouping is a really good thing to know. I encourage you to use this one very often. So this kind of goes back to the idea of ordinate dimensioning, where everything is referenced about one location. So when you dimension, I encourage you to start by grouping per a reference point like this, and then based on the application, modify this based on the characteristic views, and then based on the critical dimensions and things like that. You can modify it then. But when you start, group the dimensions. So this is, I would say, somewhat ironclad. You want to do this, and this is going to make a lot of sense too when we talk about tolerancing, because we're going to study stack up error and stack up analysis, and we will study why grouping reduces the amount of stack up error. So like I said, the grouping really depends on the design intent. Okay, so for instance, if you look at these 2 examples, they both communicate the same thing. I can figure out this length by subtracting this from that, and I can figure out this length by subtracting this from that. So they both tell me the same thing, but they actually communicate something different, because when I send my drawing out, the machinist is only going to measure what they see on the drawing, and then they're going to ship it to me. They're not going to measure this. Or in this case, they're just going to measure that, and then they're going to ship it to me. So the reason these 2 communicate different things is because maybe this was a critical dimension, right? What do I mean by critical? Again, like something has to slide inside of there. It has to slide and has to fit perfectly, or it has to clear, or it has to interfere. This could be a critical dimension. So if I dimension it like this would be wrong, and this would be correct. And then vice versa for that. So what I'm trying to say is how you group and how you dimension really depends a lot on the critical dimensions, on the critical features. So you have to understand, as an engineer, you have to understand what this part has to do and how it fits on the greater assembly. Because the machinist is not going to really care. They're not going to care, if your machine works. They just have to figure out how to machine what you're specifying. So understand the responsibility that you have. You have to design a product, a machine that can be handed off to the shop floor and can run and can be consistent. That's the goal. That can produce this many parts per hour by just pressing a button. That's what you're given, and that's what you gotta figure out. That's what you gotta design. So try to make sure that when you look at this, try to make sure that you design, you specify dimensions per per the application. You cannot cross a dimension line, but you can cross an extension line. So this one is actually very ironclad. You can Google search detail mechanical drawing. This is something that you almost never break. So, for example, when we looked at this, we crossed extension lines all the time, and that's okay. But we never crossed a dimension line, the line with the arrowheads. Okay, so that's what this is saying. Don't cross a dimension line, but it's okay if you cross an extension line. This one is a bit gray. This one is not so critical. It's okay to break this rule. This one says that keep the dimensions between the views. So for example, you see this 2.5. I could have placed this 2.5 above, okay? But I didn't because I wanted to keep the dimensions between the views. Same with this 1.5. I could have kept this 1.5 on the side here, but I didn't. I kept it in between because I want to reduce the travel distance to see how these features correlate between the views. Now, this may not make a lot of sense on something this simple, but most drawings are not this simple. They're super complicated. They're like some spaghetti job of lines, and it can be really confusing to try to correlate certain lines that are very far away. So you want to minimize the distance by keeping the dimensions between the views. This one just says that when you show your dimensions, make sure that they are horizontal, like this. Don't display them like that, where it's vertical. It's got to be horizontal. Again, this is just per the ANSI standard. The ANSI standard says this. Other standards may say do that. A bolt circle diameter is what you see here, where you have a bunch of holes on a center line that is a circle. Okay, so you may come across this feature quite a bit, especially if you look at flanges, right? Large flanges, this feature is very common. To dimension this traditionally would be a lot of work because I'd have to put an X and Y dimension on each of these holes and I'd have to put a radius on each. So that's almost like 9 or 12 dimensions and it can be a mess. So instead of doing that, you can specify these 3 holes with just 2 dimensions as you see here. First, you gotta define the bolt circle diameter, which is BCD, and then you specify a note to say equally spaced on BCD. There are many other ways of doing this, but this is just one way to really clean up and consolidate your drawing so that with just 2 dimensions, you can fully define 3 bolt circles that you see here. The next 2 slides I'd say are pretty ironclad. Duplicate dimensions and missing dimensions. So let's talk about this. This is saying to not include duplicate dimensions on your drawing. For instance, you see how there's a duplicate dimensions here? Because if you're telling me this is that size, and you're also telling me it's this size, and you're telling me this size, you're telling me more than what I need to know to complete this. So this kind of goes back with the sans serif fonts. Don't tell me more than what I need to complete this drawing. Just tell me exactly, just enough, so that I can successfully machine this product to the specifications. So there's a lot of reasons why this is bad. One is that, like I said, it's over communicating, and then 2, it causes contradictions in the geometry. When you study GD&T and tolerancing, you realize that this causes internal contradictions that make it impossible to fully define, because it's like saying make something 1 inch and then make it 2 inches at the same time, and that just causes a lot of problems. So what this is saying is don't include duplicate dimensions, but sometimes you want to say how big something is. For example, you want to say this is 45 degrees. Most of the time that's when you feel like something is confusing. You're looking at a drawing and you feel like what you specified is confusing. So to avoid that, what you do is you put parentheses. You say this is a reference dimension. When you have parentheses, it means it's a reference dimension, and it means it's a duplicate. Okay, so this tells the machinist that I don't need you to measure this, measure that, but you don't have to measure this. I just included this dimension so that it helps you machine it better, or it helps reduce confusion, because maybe the machinist has their end mill at this location and they prefer to know the angle as opposed to that, so they can just run off at the angle or something like that. So just yeah, so just be aware, if you do need to include a duplicate dimension, just put parentheses around it so that it becomes referenced. Similar to duplicate dimensions, you don't want to have a missing dimension. Okay, you don't want to have a missing size or specification on a drawing. And you may sound like this is trivial, but it can be an expensive mistake. For example, let's say the machinist is running their job on a CNC machine. And remember, like I said, setup is everything in machining. That's the most expensive part. You gotta chuck the part in a tool zone, then you gotta zero in with your end mill, you gotta do the programming. You cannot just swap that setup with another job just like that. So let's say the machinist is running this job and they realize they don't have this dimension. So then they call me, and then I'm in a meeting. So then I call them back, and then they're at lunch. So then there's like this phone tag going on, and there's no production going. So you have an idle operator and an idle machine for hours just because of a missing dimension. So this can be a bit of an issue, all right? So that's why you always want to have two people check your drawing. Have two engineers look at it so you get a second pair of eyes and try to avoid these mistakes. When we go over examples, I will show you how I like to avoid this mistake by visualizing how this is going to get machined in real life. SOLIDWORKS doesn't really have a good tool for detecting this, so you still have to kind of you have to rely on manual techniques. But again, try not to have any missing dimensions. When you start to dimension, I said that you want to go by grouping. But another thing you want to keep in mind is to determine the characteristic view. For instance, when you look at this notch here, you got to ask yourself, where is it best described? Is it best described on the top view, the side view, or the front view? What I mean by that is, where is it easy to tell? Can you really tell what that notch is on the top view or the side view? I can't really tell. It's hard to say. But on the front view, I can see, oh yeah, that's exactly what it is. It's some sort of notch. So this is saying dimension the features on their characteristic views. That's why you see all the dimensions on the front view for that notch. Or for example, on this hole, it's best described here. So this is where I will put the dimensions for that. Okay? Same with this. See, this is best described here on this view, so I'm dimensioning there. This hole is best described there, I'm dimensioning there. I'm not dimensioning the hole here, okay? Or this staircase, it's best described here. So this is just saying that on a drawing, if you're not sure where to start with a ref point and start with the characteristic views. So here's an example. You see, these dimensions were moved here because this staircase is best characterized in this view. This recommendation is saying to keep the dimensions outside the projection. So see, this is the projection. This is where the object is. It says don't put the dimensions inside like that. Keep them outside. The idea is to avoid confusing dimension lines for visible lines. We want to think that the inside is the object and everything outside of it are like measurements, are like gauges. Okay, that's the idea. And I was guilty of this for a long time. I did not realize that this was an issue until my third year after making hundreds of drawings. That's what I'm saying. I think it's a good idea to experience different departments, experience different companies for a couple of years, because otherwise you'll keep doing the same mistake and no one's going to tell you you did something wrong. You're going to only get better by exposing yourself to different engineers, to different professionals, and at some point you're going to understand what's good and what's bad. And a lot of times I've noticed that some of the best advice I'd received were really from internal machinists and technicians. A lot of times when I send a drawing out to an external machinist, I just hear, oh yeah, go, yeah, that's all right, we can do it, it's going to be fine. But I never realized that for years I'd make bad drawings. But it was really from internal customers that would really tell me, hey, it'd be so much easier if you do it like that or like this. So I encourage you to get a little bit more exposed to different engineering departments so that you get a much stronger understanding of what's good and what's bad. This one is about staggering dimensions. When you have a bunch of dimensions on top of each other, don't do this because it's hard to read. Sometimes on very long products, you follow the dimension line and then you mistake it for another one. And also, you create a lot of dead space. You see the dead space here? When you zigzag, you reduce that dead space. You can condense this a lot more, and it's a lot easier to read. So you can either do a zigzag or you can do a staircase, but don't do it aligned like what you see here. Version control is also really important. This is about understanding the changes of a drawing. Anytime you create a drawing, usually it starts with a dash or an A, and then when you make a change, you have to update this. Let's say you make a change, you change a dimension or a line. You have to update this rev from an A to a B to a C and so on. Especially if you send it out to a machinist or you send it out to a customer. A lot of times it's very dangerous to make changes to a drawing after you've sent it out to a customer or a machinist and not update the revision. And it's easy to forget. I sometimes did that, and that was a really dangerous way to work because now you have a drawing in the shop floor with the same version as the latest and greatest. They have the same version number, but they are different drawings. So now it just creates all kinds of confusion in the shop, you know. So remember to update this number as soon as you make a change, and make sure to contact the machinist to say, hey, an update was made. Nowadays, a lot of version control is done through product data management. And a lot of this software kind of looks like this. A lot of this version control with the revision is done automatically. Anytime someone makes a change, this updates. And you have to do that, especially when you work with a lot of different engineers, a lot of different associates who are working on the same assembly. You have to have a computer update this automatically. But not every company is set up like that, and because of that, you have to rely on your memory. You have to rely on making sure that as soon as you make a change, you have to update the letter manually. And I know it's tedious, and I know it's prone for mistakes, but if your company does not have a PDM set up, that's what you have to do. In typical software development, they use something called Git control, which is what you see here. And it's essentially the framework for PDM technology, but the way it works is you have a master copy, you branch off a copy of that so you can modify it, then you commit it back to the master, and you make sure there's no merge conflicts, because something could have been updated during this time that may conflict with what you did. So you have to really mix and match and make sure that everything can maintain functionality from the master and your branch, and you continue on, and then someone else can branch off and continue their work. So you can see that this can turn into a nightmare when you have thousands of people working on the same file. So there could be a lot of conflicts, and it can really be confusing as far as how do you maintain the version between these different files. So again, this is why it can get really complicated, and why the more version control you can use, the better you'll be, as opposed to manually remembering to change revision numbers. This just talks about scaling. A lot of times you have a product that's so large that you can't fit it on your sheet of paper. So what you do is you scale it down. You can scale anything down in different scales. You can have something 1/2, 1/4, 1/8 on the same drawing. But the dimension does not change. See, the number does not change. All scaling does is it just changes the size of the diagram so it fits on your sheet. Finally, the last point is to understand your role in engineering. This is more applicable for large companies. For large companies, engineers have a very specific role. So I've heard a lot of engineers complain about this in meetings. This is why I added this slide. What this is saying is, if you're a manufacturing engineer, specify the manufacturing requirements. If you're a product engineer, specify the product requirements. So for example, if I was a product engineer, don't tell me to use a 1/2-inch drill, for instance, because I may not have a 1/2-inch drill, right? I may just have a 1/4 inch drill, and I may decide to circle interpolate to cut that hole. Or I may use an EDM machine. Or I may use, some sort of 0.75 drill that I ream down to 0.5 to get this done. So, as a product engineer, what you should do is communicate what you need for the assembly to be functional, to be successful, which is just 1/2 inch. I need a 1/2 inch. I don't care how you do it, just give me a 1/2 inch and I'll be able to complete my assembly. So the manufacturing engineer is going to understand how to build the product. The product engineer is going to understand how to build something that can be assembled for its application. Again, this is mainly relevant for large companies. In smaller companies, you got to wear a lot of hats, and it's normal to be the product engineer, the project engineer, the design engineer. Okay, it's normal to wear all those hats and do everything, but in larger companies, you become more specialized into a tiny part of the project, and sometimes you will hear these complaints in meetings. So let's take a look at some of the errors in dimensioning that we just studied. So take a look here and try to identify some of the errors. So let's take a look. Remember, we said we want a little bit of a gap at these locations. We also said not to break, not to cross a dimension line like you see here. We also said per the ANSI standard, this has to be horizontal. Also, we said don't put the dimensions inside the view, keep them outside, so they're like sensors. And then here you probably wanted to add a little bit more distance in between these two dimensions. So here's the solution to that example. Okay, let's take a look at this one. Alright, so as you can see, this is not aiming towards the center. You see how it's missing that? Okay, gotta be careful. Also, you see how it's underlined? That's not good. The ANSI standard says it's got to look like that. When it's underlined, that means we're using the ISO standard. That's okay for the ISO standard, but for the ANSI standard, it's not okay. Also, you see how these are connected? Nothing should be connected between views. Each view is its own thing. It's okay to connect a center line. You do it all the time, but within a view. You never connect anything between a view. Also, again, here we're crossing a dimension line, which is not good. This one is about duplicate dimensions, okay? So check to see where duplicate dimensions are found. Like look at this 40. It's the same dimension. Why are you putting it twice? You don't need to. 200, 200. You don't need to do that. Okay, so take it off. Take it off. Take it off. Only communicate what you have to communicate to produce the product. Here's another example. Okay, it's good to get as much practice as we can so we become better at this. Because as you can see, there were quite a bit of rules. You want to get used to this language, to this technique of dimensioning. So now I'm going to do 3 examples. This is from the start file, and this has 3 examples. A little bit of symmetry over here. Positive cylinder, okay, a very common piece of hardware that you'd machine on a lathe. And finally, just a regular orthogonal object with an incline. So I'm going to practice all 3. And you may want to, again, update the template. So type in your name, capital letters, like we talked about, so that this is all set up and we're ready to go. Alright, so to start, we're just going to use the Smart Dimension tool. And we're going to first look where the ref point is. This is where all the dimensions are going to pick off from. And also, we're going to try to identify the characteristic view for this notch. And as we can see, it's all done over here. So here's what I'm going to do. I'm just going to start where the ref point is. And I'm just going to start adding dimensions, just like you see here. As soon as this changes, see this line, as soon as it changes, I just add a dimension. Okay, then I see it change over here as well, and I'm going to, guess what, I'm going to add a dimension there. Alright, so I did that in the horizontal direction. Now what I'm going to do is do the same thing in the vertical direction. So here's my ref point again, and I'm just going to keep building till I reach the top of this structure. I've defined the front view, but I need to define the depth, right? And I can't really do that with the front view. So I gotta pick either the top or side view. So I can do either or. I'm just gonna pick the side view, alright? I feel like this is a little bit best described. But it's not a big deal if you pick the top view. It's really not a huge issue. So Alright, so I need the depth of this, and I need the depth of that. And I'm going to hit escape, okay? So to see if I have any duplicate or missing dimensions, here's kind of the way I like to do this. So if you remember from a previous lecture, milling is one of the most common ways of machining a product. So when you're starting out and you're not sure how they're going to produce the object, pretend they're going to use milling, and that's going to help you determine if there's a missing dimension. So in this example, that's what I'm going to do. They're going to start with an oversized block, meaning I need the width, height, and length. Okay, and I hold control to select them. Then they're going to mill this little chamfer here. And to do that, they need to know this position, that position, which they do. They know this position from here, and they know that position from there. What I'm essentially doing, I'm looking to see if I have the Cartesian coordinates for each of these points. What I mean by Cartesian coordinates, I mean the x and y position. If I have the x and y position for each of these points, then I have no missing dimension. Okay, so then they're going to keep going up until 2. So I'm trying to figure out how they're going to machine that. So they're going to take their end mill, go all the way to 2. Alright, and down to 1. So they're going to use that value again. They're going to take their end mill in this direction now up until 1, and then shave off the back from the center line until it's flat. So as you can see, I did not have to select anything more than once, and I did not have any dimension that was not selected. So I selected everything exactly once, meaning I do not have any missing dimension, and I do not have any duplicate dimension. Okay, if I had a missing dimension, it means I would have been stuck. I would have been like, hey, I don't have the y position at this coordinate or at that coordinate. I don't have the right numbers. And I didn't select anything twice to say I have a duplicate dimension. So this is how I check to see if my drawing is good. On the next example, what we have is some sort of turning job, and we're going to use the same principle. We have the ref point, and we're just going to start dimensioning from the ref point. Anytime this profile changes, just add a dimension, just like that. Okay, so I've added the horizontal dimensions. Now I'm gonna add the vertical dimensions, and what I'm doing is I'm making sure to zigzag. Do you see how I'm using the zigzag technique? This is the same diameter as that, so what I'm gonna do is I'm gonna select both, and I'm gonna let the extension line hover over. This way I don't have to dimension twice. I dimension once and it's gonna communicate that both are the same. Okay, and then for this diameter, I'm just going to dimension it here, just because I don't want to cross through the entire piece, just to show that. So as you can see here, I did not do this, you see? Remember, we talked about that. We said this was confusing. I did not align the dimensions. I'm instead doing a zigzag, so I take advantage of the dead space, just like you see. Okay, so I've added a zigzag here, and then here I've added a staircase. Okay, so it's nicely spread out. But another thing you might need is the symbol. So the symbol would be here. See, that's the diameter symbol. Again, later we will learn how to do all this automatically. I'm just showing you how this is supposed to look. Because you got to make those decisions. You got to decide, how is this going to lay out? How is that going to look? So you are constantly making decisions when you build these. You're trying to decide, alright, first of all, does it make sense? Second of all, can it be machined? Will the customer be able to use this easily? Okay, so here's the dimension here. See, this is what I did not like. I prefer that you do this instead, because you utilize the space a lot better in this fashion. Just like that. We have a hole here. So remember, we said holes need a leader. So I'm going to spell this as a leader, just like that. Another thing you'll notice is this radii. I actually did that on purpose. A lot of times it's hard to lathe a sharp corner. Okay, there's always going to be a little fillet on the lathe insert. The lathe insert is going to leave a little residue from the fillet. And I've heard some machinists complain about that. They say, hey, can you give me a little tolerance in here? Can you give me an 8,000ths radii tolerance so that I can leave a circle? And personally, I never had a problem with that, because a lot of times these glands, these are very famous or common in mechanical engineering. These are O-ring glands. You slide an O-ring inside so that it can seal. So personally, I didn't mind adding a fillet because it kind of cushions the O-ring. It lets it sit there nicely and maybe even prevent a tear. So I'm usually pretty cool with adding that fillet. And in this case, there are 4. So I can go ahead and just add a little fillet here. I'm just going to put 4x. Again, all this stuff we're doing manually is going to be automatically done later. So there it is. Okay, so this one is just about done. All right. Finally, what we have in this example is a lot of symmetry. And the reason I want to go over this is because I had to deal with this many different times in the industry. You work with symmetry quite a bit in design. So what I'm going to do now is just create a center line in between the symmetry. Okay, so I see it's symmetrical there, symmetrical here, and symmetrical there. And I'm going to talk more about how you add center lines during the part drawing lecture. But for now, just follow along. Then I'm going to add a note with a CL symbol. See the CL symbol? That's the centerline symbol I talked about. And when you put it on the center line, it communicates that the product is symmetrical about that center line. So that's what it communicates. But like I said, there's another way of doing that by adding a datum feature. You can add a datum and say all dimensions symmetrical about datum A. Once you do that, you can now dimension the objects in the center. For example, I can do this. I don't need to dimension that and then have everything biased on one side of the model. I can keep everything centered because I'm telling the machinist to center their end mill at the center line. So what's nice about this is that the error is symmetrical. Okay, if there's machining error, it's symmetrical. It's not biased towards one side of the machine. So this is why when I see a symmetrical object, I take advantage of this and dimension like this because it's so much more effective. The next thing you gotta kind of identify are the characteristic views. So we already talked about that. In this view, you can tell that these 4 holes are characterized in this view, so I'm going to dimension them there. In this view, this hole is best characterized and same as this notch. In this view, this lip is best characterized. So I'm going to dimension all these items where they're best characterized. Okay, so this one's going to go here. This one's going to go there. Okay, so this hole is going to be characterized from here. And we need the diameter of this. And we need the diameter of this as well. And there's 4, so we're going to pick 4x. And we're going to put a dimension for the fillet as well. There's 4 of these fillets. When it's a small fillet, usually you don't put a center line. You just kind of assume it's there. But when it's somewhat larger, you usually include it. We need to specify this feature. So I'm going to add a dimension here and a dimension there. And we're going to, oh, actually there are 8 of these. 1, 2, 3, 4, 5, 6, 7, 8. So we're going to change that to 8. Okay. And then let's see, we gotta define this. So this needs to be defined. What about the height? The height is gonna be here. And this lip needs to, okay, since this is symmetrical, we can communicate. Well, this would be duplicate. This 16 is the same as that one, so we don't need, but we do need the height. So that looks pretty good. Okay, so let's see if we have any duplicated or missing dimensions. I need to machine this. Let's say we're milling this. We're going to need the height, the width, and the length. All right, so we got the cube. Then we have some sort of notch that's this wide. We already know where the center is. We're going to center on our end mill. Go this wide, go this high, and then with the hidden lines here, we're going to cut all of that in one shot. It's going to be a through cut. Then let's see, we got to cut these pockets out. So we're going to move our end mill up to here. Again, I'm trying to find the Cartesian coordinates of each of these points. Let's see if we can find this one. We know where this one is because we know the width of this. We know what this is, and we know it's centered, so we can do this minus that divided by 2, and we know exactly where this point is. So we know where that is, we know how wide this is, and then we are good to go on this shape. We also know what the fillet is based on that. We need to now cut these 4 through holes. So to define a hole, you really need 3 things: the X position, the Y position, and the diameter. We know the diameter here. We know the X position and the Y position because, again, because these are centered, I can fully define this on this projection. Finally, we have a through hole here. We need to know the diameter. We know how high it is, and we know it goes all the way through because of these hidden lines. We don't need to know the we don't need to know the X position because we can see that it sits in the center of that center line. So that was one of the assumptions that we talked about. So as you can see, I did not have to double click any dimension. I did not need any dimension, so I do not have any missing, and I do not have any duplicate dimensions on this projection. So when you're done, you're gonna get a little bundle or binder like this with what we did, okay? You'll see the clean values and dimensions that we learned and things like that.